If wishes were fishes, if all we had was a situation where all of our data was normally distributed and we had a nice big data set, then we could just use the empirical rule all the time. We could, for instance, have a mean of 1.4, and then we'd be able to say 68% of our data fell within one standard deviation of the mean, and so on and so forth. But that's just not the way that the world works. We are working with a variety of distributions, and some of them, are more extreme. They have fatter tails, as it were, than the normal distribution. And we'll give you a visual representation of that here. And this motivates and sets into play, like, what is Chebyshev's theorem, and, why do we need it? And what Chebyshev's theorem does for us is it allows the real convenience of knowing roughly how much of your data should fall within a number of standard deviations of the mean, which is really the bread and butter of the empirical rule, but it generalizes out to any distribution, no matter maybe how extreme that distribution is. And here is a visual to demonstrate why that would be potentially useful. We have the normal distribution here with a mean of 0 and a standard deviation of 1, and we have this other distribution called the double exponential. It's also symmetric. We've set it so that it is 0 mean, it's symmetric, and it's centered at 1. What we find is that particularly in the tails, there's far more happening far away from the mean for the double exponential than there is for the normal. We can see that it's kind of, the curve is higher as we are farther away from the mean value. The empirical rule, while it's really lovely, it just wouldn't work for the double exponential distribution. And that's where Chebyshev comes in. And I'm not singling out the double exponential. I'm saying what's nice about Chebyshev is it works for absolutely any distribution that we want. One caveat, Chebyshev's theorem only works when we're dealing with z-scores or standard deviations away from the mean greater than 1. So keep that in mind. And we're going to walk you through, hopefully now that you understand what it is and why we would be interested in it, the two variations of questions that you're going to come across. Lines on Clay users, you're in luck. We've kind of set it up for you. But this kind of question, or this flavor of question, comes into play quite a bit. Here's what you do. You first set your mean, then set your standard deviation. Now, very often by set, what I mean is you're being asked a question, say out of a textbook or what have you, and you are just entering in the values from the textbook, right? And here's a useful way to think about what we are right about to do. Supposing you saw a grocery item and there was, like, the items are apples and oranges and the cost is $128 and $107. Well, one way I could go about this is say, well, let's go from grocery to cost. How much is an apple? And you'd say, okay, well, I'm going to go from left to right. I'm going to look up apple, and then I'm going to say $1.28. Or I'm going to look up oranges, and then I'm going to see it's $1.07. But the other way that I could do this is in reverse. I could say, which grocery item costs $1.07? I would start here, and I would go back to oranges. Which grocery item costs $1.28? I would start here, and I would go back to apples. This is how a lot of these questions get posed with Chebyshev, and it can be really confusing for students because they feel like they kind of learned it one way, and then all of a sudden they've got to reverse engineer what they've done. It's really just kind of rearranging some math terms. For instance, if we had a mean of 8.4 and a standard deviation of 19.73, doesn't matter whether it's population mean or sample mean. If I wanted to ask a question, or if I was asked a question, like if I put in a certain number of standard deviations, how much of my data am I guaranteed to get? And so I've put in, say, 2.93 here. And what Chebyshev does for me is I enter in those values in the formula and says a range that spans 2.93 standard deviations in either direction of the mean will hold at least 88.35% of the data in your data set. So given your mean of 8.4 and your standard deviation of 19.73, at least 88.35 of your data will live between negative 49.41 and positive 66.21. You can see where, like, there's lots of little questions that can be asked around this kind of thing. The other way of doing it, though, kind of keep this grocery item thing, like apples are $1.28, but it's $1.07 for oranges. Another way of saying is, like, how many z-scores do I have to go in order to guarantee a certain percentage of my data? And so if I said, well, I want to make sure that I have 92.3% of my data taken care of regardless of the distribution, Well, you need 3.60 z-scores to make that happen. It's just rearranging math terms to make that come into play. And so our Chebyshev calculator does all of that for you. But what we wanted to make sure is that you understood fundamentally, like, hey, why do we need Chebyshev? What's going on when we're doing it? And how is it or why is it that there are kind of like two types of questions that we might get asked when it comes to Chebyshev? So, hey, hopefully that helps.